Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to introduce Neil Lawrence as today's colloquium speaker. Neil is a professor of computer science and neuroscience at the University of Sheffield in the UK. His main research interest is machine learning through probabilistic modeling, and he works both on the development of new models and algorithms and their application to some interesting problems. And in particularly, he's interested in personalized medicine and computational biology, but has also done some great work on computer vision, computer graphics, and speech. He's widely known in the machine learning community and very active. And
he's had great students.
Amazing students, yeah, I don't know. Exactly. Great students, yeah. That was part of the accomplishment. And he was a program chair for NIPS last year, so if you didn't like the program, it's his fault. And he's general chair for this year, so if you don't like anything else, it's his fault. So without further ado, he's going to talk about Gaussian processes for personalized health.
Thanks, Niccolo. And it's very true, I've had excellent students, Niccolo amongst them. And one of the problems you get when you have very good students is you start knowing less and less about the things you apparently are supposed to do. So what I thought I'd do today is talk a bit about what is been the main motivation for the group. And actually Niccolo's PhD project was a key important part of being able to make claims that we're doing this. I don't think we are doing this yet, but it's sort of speculation and ideas about what the challenges are for personalized health. And when I say personalized health, I mean, we're doing little aspects, trying to piece some things together. There'll be one example that isn't really so much personalized health. But I'd like to sort of pull everything together, all the sort of data we can get about people and use it to predict health outcomes. And I thought this was an interesting idea. But before I sort of go into the background to that idea, I just give you my perspective on what it is I mainly do, which is sort of machine learning. So I know not everyone has a machine learning background, so this is a sort of broadly non-technical talk. But I very much view machine learning as combining data with a model to make predictions. And I think without a model, you can't do anything. So your model is assumptions or based on previous experience. So in some fields, your model may be driven by physics. In machine learning, it's based on old data. And I particularly like the idea is that it encodes something about our beliefs of the regularities of the universe, which we sometimes see as inductive bias. Things like smoothness. So one of the things, I should actually always test doing this. This used to work in an interesting way, and it probably doesn't work in a very good way in the United States, but this will be a live test. When you Google for, have I got internet? Oh, nothing comes up. Certainly in the UK, when I have internet, I think I've lost the internet connection. You see what people search for, and the big thing that people are searching for in terms of the suggested things is patient data protection. That's what tends to be the sort of first suggested search up. So here it's patient information, patient data analysis, patient data collection sheet. So you tend to see terms like this. And it's sort of something that's more on people's mind is analyzing patient data. Here, apparently, protection is less on the minds of people who are searching. But what that brings to mind for myself is whether I actually even want to get involved in this domain, because I think it's a very complex area. So I had a while ago, about 8 years ago, I had a cycling analogy that made me think that this was an interesting thing to do. In the world of anonymity, this is my picture of where we are at the moment. This is, I think, an 1880 picture of cyclists going down a street. And this is how it feels in terms of the protections we have now and the lack of information people know about us outside. What's going on for us is the invention of the motor car. So I cycle a lot, and I really don't like cars. I particularly dislike cycling in the United States. It's a very unpleasant place to cycle. And that's because the things are weighted towards the car. The car overrules the cyclist. But there was a time when things were weighted more towards cyclists, and cycling was more present. We're going through a similar sort of social change with our data, with our anonymity at the moment. And it sort of worried me a while ago that if I were to get into this area, I would have to deal with all these things like privacy and so on and so forth. And this intimidated me, and I decided I wouldn't do it as a result. Until I kind of thought of this. This is the UK history of registration. And in the early days, they had this thing called the Locomotive Act 1861. Limit the weight of steam engines, this was steam engines at the time, to 12 tons and the speed of 10 miles an hour. Limit in 1865, a speed limit of 4 miles an hour, 2 miles an hour in towns. And this provided for something called the Red Flag Act. So this was provided for a man walking in front of steam engines, waving a red flag to warn you that these steam engines were coming. It's actually more for horses than cyclists, but it was to deal with the effect that these objects had. This was kind of reasonably restrictive for the development of the automobile, and you may know, although at the time Britain was the center of the industrial world, the modern automobile was invented in Germany. And in the end, it was overturned, and it was replaced with something like this, the Highway Code. In the UK, the Highway Code, what's it called here? It's the, there's an equivalent document here that you have to read and get examined on for your driving license. And this is the UK version. It was introduced in 1930. I kind of view us at the moment that we're in this difficult regime of developing legislation where we don't even know the technology is going. The equivalent zone they were in 1860. And the development of the Highway Code was actually about a debate to allow us to move forward and sort of balance the rights of the cyclists, people with horses, people with cars, and it's an evolving document. And so when I sort of thought about that, I thought, okay, great, so that will happen, some process will occur like that, and everyone's going to be happy in the future. So I'll start working on machine learning, personalized medicine. That was about 6 years ago. And I see very little progress in this domain. So one of the things that I'll try and bring through, and as I've spoken to people today, I've brought through is I found myself increasingly being worried about all the things that I didn't want to get involved with, and that's why I didn't want to do personalized health, because of problems of invading people's privacy and what it meant to create algorithms that could predict someone's health futures. Okay, so there's issues of who owns our data, and at the moment it seems it's like finders keepers, like the kids rule. You know, if I find the data, then it's mine. I can do whatever that I like. How ownership proliferates, and what data protection offers. I think definitely I would argue that UK and Europe are well ahead of the United States in recognizing data protection as a right, privacy as a right, and I think that that has to come here as well. But I don't know what the rights are, and I don't know that we've got the correct frameworks in place or how those rights should evolve. So what does current data protection offer? Who has the right to share our data, and can we withdraw the right? The last thing seems key, that once we've given someone the right to own our data, we have no right of withdrawal of that right, and that has a lot of implications. So in the UK, there was this NHS Care Data Information Scheme. So you may know we have a National Health Service, so that means we can have like national databases. Funnily enough, we don't have very good national databases. But this was a scheme to sign up to a national health database, which everyone was going to be signed up to, and you had to explicitly opt out if you didn't want to be involved. And I was really looking forward to this, because I sort of thought, well, when this is imposed and it's done in the right way, because these clever thinking people will work out how to do this, we'll suddenly start getting access to these very large data sets that will allow us to start predicting health outcomes. It was a disaster. It was utterly mishandled. In terms of the press, basically, I don't even know what its state is currently. It's one of those things where it was just too depressing to read the articles about how it evolved, and so you sort of ignore those news items. But this is one I dug out. So it's 18th of April, 2014, so it's just over 16 months ago. And the reason it was mishandled was because they never closed off the option that they were just going to be selling this data that people were going to be giving freely to health insurers. They wanted to make money out of this. This is our government. Not the, well, it was unclear what they wanted to do. Some people say they're not going to do it, but then there was evidence they were trying to do this. Extremely badly handled. So one wonders if they've learned the lessons, but it's not clear that they have. And that's one reason why, instead of just talking about technical machine learning stuff, I've moved much more in this direction, because it's depressing, the extent to which things are going wrong. So this is my sort of image of a country that's sort of going through this transition. I would have loved to have visited Beijing when it was all bicycles, but it isn't anymore. It's got Ferraris and stuff in it, and it's apparently car-dominated. So I like this image of this juxtaposition of the Ferrari and some bicycles. This is Beijing in 2011. you know, I don't know what the right way of legislating for data, but I know at the moment we're heading in the wrong sort of direction. That's Beijing today as well. Okay, so probably many of you already know what's changing for medical data. What got me into this, and in fact Nicolas' project as a PhD student was about genotyping and had the potential to introduce epigenotyping into trying to, well, most of my work up until then had been on the transcriptome, but I tend to think of the transcriptome as a detailed characterization of the phenotype, a way of stratifying patients that I can do in a data-driven way. And Nicolas' project, we were trying to associate, doing EQTL studies, so associate the transcriptome with different genetic mutations. But it was sort of the first step in a direction where I was interested in expanding that idea, and we still are, and working towards those methodologies. We don't have them all in place for doing what I think of as massive unstructured data sources. So whatever data you're interested in, everything is phenotype. All data should be assimilated within this system. The reason I started moving more towards the regulation type ideas is I actually think, we can't do this today, but I see a technological path forward to making me believe that we'll be able to do this. People will be able, not us necessarily, people will be able to do this in the near future. Assimilate large unstructured data sources, some of which I'll briefly mention as we go forward, in order to predict people's future health outcomes. Now I realize that we might be able to do it. I kind of find the implications quite frightening. So I use this, I give this talk to clinicians sometimes, so I like this example a little bit. This is there's an open street map in Sheffield, of Sheffield University, of where you can actually see right, where's it gone? Glossop Road, I can't even find my own university. The Hicks Building, Octagon Centre. Yeah, this burger here is John's van. It's a mobile burger van. I don't know if they don't have them so much here. You have very fashionable hip street food. This is a mobile burger van of a guy who sort of makes bacon butties. And this is the sign outside his van. It's right outside our stats department. And it says you can get a bacon and sausage butty. That's a sandwich with bacon or sausage in. Not the highest quality bacon or sausage. And a large tea or coffee for £2.10. Now that is about $3. Sheffield's got good prices. So it makes you wonder, well, do the people who are in the stats department, you know that this van exists, you can get this open data, are they going to have an increased risk of heart attack as a result of this type of information? Well, that's obviously a total speculation, but this is John's van, and you can follow John's van on Facebook and Twitter. In fact, it was stolen and it was recovered via Twitter. There's a 10% discount also for NHS staff, which is hospital staff, so you might also worry about hospital people. Now, the question is, can information like this feed into such a model? The answer is, of course, well, I don't really know. If someone follows John's van on Twitter, if they're retweeting his offers when he's selling bacon butties at £2.10, maybe you can. But it's just part of a picture. It's the sort of information that humans are very good at assimilating, weighing up, maybe not predicting in a well-calibrated way, but we're happy to assimilate the information and say something about what it means. Probably, if we're all well-trained statistically, not very much. But what about other information if this is just part of a larger picture of how someone behaves? They follow John's van on Twitter, but we know something about their musical taste, we know something about their exercise regime. All of these things, can we pull them all together in order to get a picture of what this sort of person's like? Well, partly, we don't really know the answer. But that's the sort of aim in order to be able to do that. That's what we'd like to do in the long term. This is very difficult and very invasive. So we don't have access, certainly I don't. At Microsoft, you may have more access to varieties of information like that. But for the moment, what we do is, sorry, the previous picture was supposed to be a picture which was a bit larger, we're interested in looking at in the research group, one of our strategies is to look in countries where infrastructure that does the sort of things that we take for granted doesn't exist. And I'll try and give you an example as I go on as to how this works. Now, I don't really want to spend time looking at people's Spotify accounts, people's who they follow on Twitter. Lots of people are doing it. It's a crowded research area. And I also don't necessarily believe that I'll learn very much about someone's health outcomes for the moment. What I'm very excited, though, is the potential to go into countries where health systems don't exist and take things a little bit more seriously and assimilate different types of data together to make predictions about the spread of disease or what likely health outcomes are. Put things in place that don't exist already. Also do it without invading their privacy. So we've become very interested in Sheffield in applying data science in Africa. And we're not doing it in isolation. We have collaborators at UN Global Pulse and the University of Makerere in Kampala. And the idea is that we can sort of use apply our ideas more readily because existing infrastructure isn't in place. So the particular thing that I'm very interested in as a solution for some of these challenges that we've talked about is what we call user-centric models of data. So I'm saying mobile phone here, but the basic idea is that the data should be within the control of the individual. So they're gatekeeping on their own data. The reason why that maps to Africa is that the mobile phone infrastructure is extraordinary, really impressive in terms of everywhere I traveled in Uganda, I had really good cell coverage. Not all countries. I'm sure the Central African Republic is less good, but countries like Kenya have already moved to mobile money. So there's mobile, you can text people money. They're well ahead in some areas in what they do on their mobile phones. So the sort of idea is, well, can you use that infrastructure to perhaps do something a little bit beyond what we're capable of doing or people are interested in doing here? Now, I'm also working with a startup company that is sort of interested in applying that on your mobile phones and allowing people to do these sort of data processing challenges in a distributed way. But I'll sort of talk less about that. But what are the challenges with this data? So I like this article. So we want to go and we want to look at large-scale data in countries like Africa and perhaps pull it together to draw conclusions about what's going on in terms of people's health outcomes. Big data is a big buzzword, and I kind of use it less and less because I think it's becoming less and less meaningful over time. But I really like this article because it captured something that I thought about big data. It's a July 2014 article, and it just said that big data proving to be a real challenge for scientists, not because of the size of the data, but because of the diversity of the data. So it's not, this article says, and I agree with it, so that's why I'm showing it, that the real challenge is not the absolute scale of the number of data points you have, but the different natures of data that you want to assimilate. So the question is, how do we do that? Well, in machine learning, the thing that's really blown up is deep learning. So you presumably have all heard about deep learning scientists. This is like an early article, like 2012, which comes after some early nice results on image processing and predicting, categorizing data and images. I kind of think it's not where things are going for the areas I'm talking about. And I want to give you a hint about why Gaussian processes are the sort of at the core of how we're doing things. So, even this is, it's got so much more press now, but this is back 2012, the New York Times, the New Yorker, Jeff Hinton going to Google, which is old news. This is all before DeepMind. And all because they're getting very good performance on image categorization tasks. And this has generated a large amount of excitement. But my own feeling is that the models that they were using for this are not going to be the solution. I think they feel the same thing. I don't think they disagree with me. So Jan LeCun going to Facebook. I even wrote an article about the change. That was my first popular article. And then this sort of phenomenon now, this is an article I wrote. So there was the AI cheating scandal makes machine learning sound like a sport. It isn't. This phenomenon has got so scaled up that actually Baidu kind of slightly cheated on just a machine learning benchmark, an uninteresting machine learning benchmark, and it makes sort of international tech news. That's a really depressing setup. What they did wasn't even very interesting. How did they cheat? It was one of these, it was a benchmark where you submit your algorithm, you get your test result, but you were allowed to submit twice a week, see your test results. So you can kind of learn on the test data. You can actually explicitly try and do that. And so in order to prevent you doing that, you only are allowed to look at the results twice a week, I think. And they looked 10 times a week or something of that order. And the reason they justified it is because they had 3 authors, so each author was looking twice a week. It wasn't like it's nothing that, it's just really dull. The article is about, this is really dull. Can we talk about something else? If I want to criticize Baidu for doing things, this won't be the first thing I'll criticize them for. I've got lots of other stuff I could worry about. But really what's going on here, where I have a problem with all this work, is it's actually not doing intelligence. The reason all these ideas are working, I mean, there are other stuff that those groups are doing that are intelligence, but the successes we're hearing about, the AI success we're hearing from Baidu, is not generating intelligence. It's what I'm trying to call, in order to categorize how it's working, emulated intelligence. So there's a common thread to what's going on here. The applications that are falling over that we're seeing big successes, these are ones where there's massive data and massive compute, and they're perceptual tasks. So if you're that interested in the task, if it's translating English to French, you can get enormous amounts of corpora of data where it's lined up and you can start doing the learning. That's not a problem. You can't do Luganda to English. Luganda is a native Ugandan language because there's not the scale of corpora. Whereas a human can learn how to speak Luganda. Well, I probably couldn't, but humans can. You can't train computers to do it because we don't have the size of data. The scale of data we're using to train these image recognition systems is well over and above what humans need to do this sort of processing. So all we're doing is we're taking humans and with a big, powerful machine is we're sort of managing to reproduce what they say. So they're all perceptual tasks, the big successes. I mean, I'm generalizing, there's some exceptions. But they're all perceptual tasks, so speech recognition, computer vision, translation, where we have enormous amounts of data, and we're managing to build computers. And I like this idea because actually we do this, there's an area I'm peripherally involved in, which is, say, climate model emulation. So people do this with climate models. They have a very expensive to compute climate model, and they don't want to compute it, so they just learn a mapping that recreates what the climate model says. It doesn't have any of the mechanism, it just tries to recreate it. And in effect, that's sort of what we're doing with these big successes, which is great because these are really difficult tasks and we want to solve them. But we're going to hit buffers because we don't have the scale of data to do this type of task for things like human health. In order to do the same thing for human health, we would have to force everyone to be sick all the time in order to acquire the diversity of data to understand the complexity of what's going on. I mean, it's just not going to happen. Health is way more complex, I believe. I mean, if we consider all the ways in which we can go wrong and the complexity of the human body, than any of these tasks. And even if we have population-scale data sets, I don't believe that we'll be able to solve what's going on with the current generation of techniques. So one illustration of that is what I call massive missing data. So again, I'm trying to illustrate a point about where current algorithms are weak. So we kind of tend to think when we're dealing with learning of missing data as a sort of challenge that we've got some Excel spreadsheet and there's some nans in it or some pandas array and there's some nans, and maybe 20 or 30% of these things are missing. That's very frustrating, and we do a lot of work typically to impute those missing values. That's not missing data because someone's already carefully collected all that information in a table, row by row, column by column, and presented it to you. That's actually statistics, and someone was explicit about trying to get the data. You aren't missing 10% of the data. You are missing 99.99999% of the things you could know about that individual. I mean, you're missing everything. All you've happened to have collected is 25 things, or, you know, in the case of a genome, however many, 30,000, a million, or whatever, your SNPs. Now, in massive missing data, things change. The typical approach in missing data is you impute your missing values. But in massive missing data, you can't do that. Imputation is totally impractical. That's because the algorithms we use have this sort of iterative approach. EM is the sort of gold standard, but most imputation algorithms are kind of like that. In EM, what you do is you make a guess for what you think your missing value should be. Then you fit your model to the data. And then you update your guess based on what your model says. And then you refit your model. That's, I mean, loosely speaking, there's a nice mathematical proof of why that's a good thing to do. But that's basically what you do. Now, that's all right if you're missing 20% of the things. But if you're missing 99.999% of the things, you fit your model to pure rubbish because you have to guess so many things. So imputation doesn't work. I mean, even at the scale of 50% missing data, you can't impute. But my argument sorry, that's just a review of EM. In very large sparse data, so the EMIS database is a GP database in the UK. It's got 39 million patients, but they only have 30% of the market. So from that I infer there must be at least 17 million non-living patients. and thousands of tests that are done at different GPs that are coded in different ways. These are actually, they're selling databases to individual general practitioners, I should explain, sorry. They're the front line of clinical interface. So you're not allowed to go and see a specialist straight away. You have to see a general practitioner, and then he directs you to the specialist. So everyone has to see general practitioners, and they store your patient record. So then, but they're often like a house with 3 doctors in it, like a big old Victorian house is my one. And they buy, they're run as independent companies, as partnerships. And so they buy in their database system from a company that says, here's a database system. Now, these companies bought up other companies until they've actually got a large scale. It wasn't planned, so there's only now 2 or 3 providers of these systems. So you have quite large databases. But of course, the data's massively sparse because we all get ill in a massively different way. And not only is it massively sparse, but within each practice, they have different standards of how they enter data, how they code the disease. It's a bit of a nightmare. So in any case, if you try and do EM for this, no, sorry, it's a medical tests.
It's electronic health record.
Yeah, electronic health record, yes, precisely, thanks. Yeah, precisely, but not properly standardized, like done in a sort of ad hoc way as it's needed. But they're very interested in sort of people coming in and helping them improve their systems. So I work with probabilistic models, and the way we denote what we're trying to do when we model these things is, let's say I have a patient and this patient's had 2 test outcomes. Well, what I have to do is but there's many more outcomes that are possible, so there's up to P potential measurements I can make on a patient, and P is, bear in mind, going to be in millions. What I need to do is I need to do this massively high-dimensional integral in order to find out what I expect that patient's outcome is, which is a bit of a nightmare, because Y3 to YP contains every test that hasn't yet been applied to that patient and every test that's not yet been invented. So, Facebook, I know, rerun their advertising ranking system every night. So that's how they deal with non-stationarity in data. They relearn every night. My assumption is that if we're going to do these sort of large-scale population-wide health monitoring systems, we will not be rerunning them every night. We will need to adapt them in an online way. So when someone invents a new test, we won't be able to say, OK, train the whole thing all again. We need to work out how to assimilate this extra piece of information in our data. So this is an interesting phenomenon, something I've been interested in for a while technically, is when P becomes N. Everyone's used to P, the dimensionality of your data set, being fixed. So there's N people in this room, and you have P characteristics, and you're not allowed to gain any more than P characteristics at any one time. It's kind of absurd when you think about it, but that's how we model data. Of course, P isn't like that. P is also like N. You could gain new features that we find things out about. We could measure you in different ways. So medical data has this property for sure. Real data all has this property. It's only in our little closeted world of how we're doing learning at the moment that we don't include for that. But there's a way out. And the way out is that friendly distribution, the multivariate Gaussian. I mean, it has problems, which we've been discussing today, but it has a beautiful characteristic. High-dimensional integrals were, one of the things that held back the Manhattan Project, why they invented computers, all these sort of things. But high-dimensional integrals in Gaussians are kind of trivial. So if this is a 10-dimensional, so this is correlated Gaussian with a covariance of this form, so it's telling us how 10 different variables are correlated, one sample. So they're these two are correlated, and this is anti-correlated with this one. So this is saying high covariance, the correlation would be high, but it's anti-correlated with this. So this index here is a color visualization of the covariance. So we're seeing high correlation between these two, or roughly, certainly, and then anti-correlation here. Now, this has got 10 measurements, but the beautiful thing in a Gaussian is if I want to know the density for 2 measurements, say these two here, it's trivial. It's simply take those 2 elements of the covariance matrix and use those 2 elements instead. That's why correlation is like a widely used statistic. It wouldn't make any sense if this weren't the case. But when you see that the first time you see that, you think, OK, clearly. But that's super unusual. No other continuous distribution I can think of has this sort of property. And this property allows us to trivially handle missing values. Like if it's not there, it doesn't affect the correlation we believe in the existing things. There are lots and lots of problems with Gaussian densities, and a lot of our research in the group is how to deal with that. Niccolò had an excellent Nature Communications paper on warping the outputs of Gaussian densities to map the phenotype better to something that's Gaussian, and that worked really well. But this property is why we kind of use them, and why when people say, why don't you do something else, I can't get my head around on the other thing because I can't handle this challenge. And I want to be able to handle this challenge trivially. The challenge, yeah, well, that's a further challenge. You then have to build, so what does this mean for the challenge in practice? If I invent a new measurement, if the world were all Gaussian, well, we wouldn't exist. But it would be really nice. We could model everything. And then we had to model a new thing. All we would have to define is its covariance, the cross-covariance between things that already exist. And we would typically define that functionally with a covariance function. And how you would do that, open challenge. I'm not saying we've resolved that, but you can do it. There's a way forward. You know the right steps. Yeah, but typically we don't use order n. We define some similarity of that object to existing things, which gives us a function for filling in those things. And the fact that it's order n is also a problem because it's a non-parametric model, so we need some way of compressing that down to some number of things that we can, yeah, these are all the, these are things we're working on and have ideas about how to solve. Yeah, okay. So this is one of the pieces of work. Also, Niccolò was, this is something Niccolò, at the end of his PhD thesis, we started looking at and have never had a chance to follow up. But Max Wiesler, who's a PhD student with me now, we keep hoping to build models that can we do recommender systems as a sort of, so recommender systems are sparse as well and have some of the properties. So rather than dive into medical data all the time, we tend to demonstrate these sort of things on recommender systems. And that's sort of ongoing work. Just briefly, why is it that this is a problem for most models? If you're interested in deep learning, I can give you a sort of quick, if you're not aware of what goes on in deep learning, the sort of things people do in deep learning, I can give you a quick illustration about, some people sense, well, this doesn't sound a very difficult thing to deal with. So this is a model I've drawn here, which is known as a sort of restricted Boltzmann machine. It was like the first deep learning model in the resurgence of deep learning, but it was shallow. So what they did is they defined this, and then what Jeff Hinton did is he stacked these things. And his science paper was about stacking and unrolling these things, and that was one of the things that triggered interest in deep learning again, but it doesn't have the spectacular results that some of these other neural network algorithms have. But in this model, what you have is you have some number of latent variables, and then you have some number of observed variables. Here there's 10. Now, just by coloring things, I'm showing you what the latent variable is. A latent variable is some characteristic we're interested in inferring. So like a typical one that people did back in the sort of 1920s or 30s would be like IQ, or these sort of other well-known factor analysis-based characteristics. And the idea is somehow the latent variable is responsible for declaring what is in the output. So PCA is a good example of a latent variable model. This model is discrete, actually. But what I'm going to do is show you what happens when one of these nodes is unobserved. So in the graph, so in the Gaussian, it just disappears. But in a Boltzmann machine, that node itself can now be drawn up here. So this node is missing. It needs to be summed out. The problem with latent variables, you have to marginalize over them. They're discrete, so it involves a sum with now 2 to the 5 terms. But when we have this one as well, it's 2 to the 6 terms. This model is actually no longer in the same class as the restricted Boltzmann machine model. So this actually is a variant of a deep model. So these models have a lot of trouble with handling missing data on the outputs. So not all model classes. This one is an interesting model class that I sort of enjoy hearing talks about, but it can't handle this sort of thing where most of these variables are missing most of the time. Okay. So the question is, for massive missing data, how many additional latent variables? Well, what you can show is that when you're assuming a Gaussian process, you're assuming infinite additional latent variables, but they just integrate out to have a Gaussian effect because of various properties of Gaussians. Properties that have issues, but are useful in this case. Okay, so I mentioned some of our work in Africa, and I'd like to sort of just show you an example of how how we try and do this in practice. So John Quinn he was a student of Chris Williams, who's a well-known Gaussian process researcher, wrote the book on Gaussian processes with Carl Rasmussen, who about 8 years ago, after he graduated his PhD, he thought he'd try lecturing in Africa. And he moved to Africa to Malaria University, and he's still there 8 years later. Just on a Ugandan salary. He's not in any way funded by charity or anything. He's just like working as a Ugandan at the University of Makerere. Apart from recently, he was also appointed jointly to UN Global Pulse. So UN Global Pulse is an organization founded by the UN to sort of do data science, because they felt they kept getting caught out by events emerging in the world that they were unaware of and needing to move resources to handle the event. So they've got 3 labs, one in Jakarta, one in Kampala, and one in New York. They're actually advertised recently for positions in the New York lab. And the idea is to try and predict ongoing outcomes, predict when troubles are occurring. So it's a big sort of interesting data science project, and the aspect we got involved with them was predicting malaria incidents in Uganda. Why is this difficult? Well, normally if you're interested in the incidence of disease, you send out large survey teams to sort of measure to what extent the disease is present in any given area. But that's expensive and difficult to design studies. You actually don't have good baseline values on what the population is in different areas. So actual well-designed studies are a little bit hard. So our interest was, can we take an area like Uganda and use information that is available, such as the number of registered cases at health centers within little departments. So each of these is like a state. And combine that with other information sources like weather, rainfall, vegetation index, altitude, and try and improve the quality with which we're making malaria predictions. So these different types of data, combining them with the same model, and we use Gaussian processes to do that. So this is the sort of the nature of these different data. So there are 7 sentinel locations where there are actually health centers that are equipped enough to diagnose malaria. Why is malaria difficult to diagnose? Well, you have to have people who are trained to look down microscopes and see the plasmodium and say, yes, they're there. The typical way it's diagnosed is people exhibit a fever, and they're just given malaria medication if they can afford it. And if they don't get better, they're given typhoid medication. So there's a lot of confounding between typhoid and malaria, and that causes deaths because people can't afford 2 sets of medication. So this is HMIS data, which is just, this is how much malaria drugs we've given out. But this data is difficult because the distribution of drugs is not done necessarily in a clean way. So you don't actually know, so there can be corruption in terms of the distribution and movement of drugs because they're worth money. So you don't know that the number of drugs that were actually, they may be playing with the data in order to sort of hide the fact that drugs are going missing. So, and then a third form of data is satellite data on rainfall. And the beautiful thing is this is sort of open data now. Sorry, that's a rainfall there. And this is temperature. And what we're seeing here is a joint Gaussian process model over all these things. And the idea is, can we sort of combine these things to improve the prediction for malaria? Sorry, the y-axis is varying according to, I haven't given any labels, but each HMIS would be the number. This is the sort of, it's going to be a exponentiate. If you exponentiate this, you'll get a rate of number of infections, apparent infections according to HMIS. And this is time along the x-axis, yeah.
You have one time variable for sort of output for spatial variables?
Yeah, 5, yeah, so you, and what you're interested in doing is trying to cross-correlate these spatial outputs together. So, and it's one of the things, so we wrote a paper on the different ways of doing that. So this is an area we're expert in, so we're like, cool, we're going to do that. We're going to solve all your problems.
So what is the axis in the last one where you combine this for? Is that just one dimension? Is that a principle?
Sorry, no, I got the axis wrong. This is the Sentinel. This is the Sentinel patients with, all patients who go to the Sentinel. This is the patients with malaria at the Sentinel disease, because they actually look at them. These are the HMIS. So these are the ones from health centers that are being reported in the different departments. And these are, this is the rainfall, and this is the temperature.
It's not yet combined into.
No. So I think, is that one where we've, no, I can't remember what that one is, so let me skip through it. We did a sort of school there. But actually, the interesting thing about that result is it didn't work. we could not get correlation between those different things to the extent that we could make any predictions. Because the HMIS data was so noisy, it's difficult to model. I mean, actually, the main thing that Ricardo's got a couple of papers. One of his papers is, so for political reasons, the president of Uganda often splits these, I can't remember whether they're not departments, but let's call them departments or states. They split them in two, because every time you do that, you create a new set of administrative roles. And if you need to repay people with favors, you've got a new set of jobs you can give. So these splits happen on a reasonably regular basis every sort of few years. And so you've got data that's being aggregated at one level is suddenly being aggregated at a different level. And these are the sort of challenges you sort of end up facing all the time. Like, how do you do that? Because you think, oh, that's great. Well, they're just going to sum. But no, because it's two different reporting bodies, and suddenly these numbers change totally. So the actual sum of the reporting bodies from the split thing does not equal the number that are in there before. So large sections of Ricardo's work were just actually solving these issues. And at one point, and we're also trying to cross-correlate across departments. So it's not just 4 outputs. We've got these outputs for every department. But we only get the HMIS statistics at a summary level, yet we've got vegetation at quite a low-grain level. So our long-term idea was that we were going to be able to take the summary level, but say perhaps how it might be distributed across the state. We just do not have the level of data and the quality of model to do this with what we're doing at the moment. So the thing Ricardo did do, which is actually, he's going to be in Uganda implementing this, is something slightly different, but related. And this is what I love about the way Ricardo did his work, because this is not my idea, that's his idea. And it's actually improved beyond this now. This is a GIF he sent me for the workshop we did in Kenya a few months back. But Ricardo, I mean, when we talk to John Quinn, what he sort of says is, you know, you can do all the modeling you like, but what people actually want is they want a visualization of where there is malaria at any given time. They don't even have that. So there was a typhoid outbreak in Kampala, I guess, at the beginning of the year, first 3 months. And you want to know where typhoid is distributed so you know where to intervene to try and deal with the outbreak. So what you sort of want is maps like this. So the illustration I'm giving you here, it contains 2 parts. This is Ricardo's idea. It's taken from economics. So to visualize what the state of disease is at any time. So what we see on the plot is actually 2 curves. So the nice thing about Gaussian processes is we can be clever about combining trends. So we fitted, or Ricardo fitted to this data, which I think is HMIS data. It's malaria cases logged scale. It's not with a Poisson because there's such a large number that there's no point in using Poisson. You can just model it as Gaussian. But Ricardo's modeling this and showing the evolving model over time, and he's showing 2 components of that model. One is a long-term trend, that's the red, and then the other is a short-term trend, that's the blue. Now, the short-term trend is, you know, it's varying over months, and the long-term trend is varying sort of over years. And the nice thing with the Gaussian process is we can decompose this quite noisy signal into these 2 trends. And then Ricardo's idea was to use something that I think he got the idea from economics, and we're going to even improve this type of plot further, which is to sort of allow people to visualize what's going on. So you do this for each state, in each state at each time. So green here means that the state of the disease is below the average of the trend currently, and it's also going down. So what you're visualizing is a plot of the rate of change, the gradient, and the sort of absolute value. Red is it's above and it's going up. And these 2 different yellowish colors are either above average but going down, or below average but going up. So these are sort of things that we feel the sort of people who are doing the decision making in the UN can kind of grasp the idea. We're actually going to change this plot.
What is the time scale that it stays in one color?
Yeah, so we're seeing these are years here. So you're seeing different points coming in probably a couple of weeks or every month or so, something like that. Yeah. So
enough time for you to say this is significant and do an intervention? Or?
I think that we're more interested, the particular example, when I was in Kenya doing this data science workshop, the thing we got excited about was this typhoid example, because those maps were evolving on an hourly basis type thing, or 6-hourly basis, something like that. They actually use what John does, I think, I don't know all the details of this, they have access to telecoms data now. So they know people's movements in Kampala from station to station. And so they can sort of try and exhibit use that, combine that with existing data to sort of say how things are evolving.
I mean, the vertical with some discrete derivative, so that's presumably over some interval that's sort of meaningfully.
I mean, when you say discrete derivative?
I don't know the vertical coordinate in that plot.
So it's continuous because one of the properties of GPs is the derivative is jointly GP with it. So you know the derivative constantly at all times, and you know a distribution over it. So the sort of things that we want to modify with this plot is that actually we've got drawn a spot here, but it's not really a spot, it's a distribution of places where we think we are. So the thing that we want to do with Ricardo when he's in Kampala is start working out how to visualize that type of uncertainty and then how to convert it to a map. So the idea is then you have some sort of spatial map. So now we're just, because it doesn't work to correlate everything, all we're doing is viewing the map over time. That gray area, we don't know whether that gray area is the right size. Maybe we need to play with that. But what we're seeing in these gray areas is too indistinct descending. It's just around the average. We're seeing the red is sort of high and going up. Green is low and going down. Yellow is, I can't remember which way around. And the idea with that is to try and extract this information that's in the Gaussian process and show it to the person. So the idea of doing these data science workshops in Africa is to help people understand how to process data. But people aren't that interested in the Gaussian processes and their clever properties. They are much more interested in visualizations that are helpful in showing them how to do things. And it sort of strikes me that or what Ricardo did, which I really liked, you can't do these things independently. You have to think about the visualization, how you're going to communicate that information, because you won't be able to sort of make the decision, let's send drugs here, based only on your Gaussian process.
So when you're making this plot, you're looking at malaria or typhoid outbreaks or something like that. It seems like the GPs are good for making these predictions if you don't know the rate of malaria in other places, but presumably you're going to be using like lots of other like covariate information, right? Like, are you using that here?
No, not in this example, because it's a sort of it didn't work to use the information in the way we wanted to use it. In the typhoid example that John's modeling, he is using some of that information.
It's very hard, like if you have more than a few variables, to do that in this GP framework, right? Because that's
no.
Why? Because then you have to model, or you're modeling the full density over all of the.
No, sorry, we don't jointly model over the covariates. We model over the response only. Yeah.
Missing a variable and knowing it.
Yeah, no, that's true. I've not highlighted that. There's a bit missing part of the story, as you've correctly identified. Yeah, so if it's a
so imputing is fine over the targets, is basically.
So imputing over and actually the thing that I didn't really show is that's how we do most of our modeling. So we tend to model the responses directly. We're not doing it in this case because it just doesn't sort of fit. But I like this example of I don't know, you have these big visions about how you're going to save the world, and in the end, you realize that the most useful thing anyone can actually have is a correct visualization of what's actually going on at any instant at the time, because they don't need your fancy Gaussian process model yet. So you have to do these sort of things along the way. Okay, so, but as you correctly pointed out, those types of models, are actually not modeling directly on the output. So this is actually the sort of type of model we're interested in. So this is a so-called deep unsupervised learning model. So what we do is with these latent variables, and unlike the Boltzmann machine before, we push Gaussian processes between each of these layers. So in deep learning, normally people build parametric models to map between each of these layers. We don't. We build Gaussian process models. So this is work by Andreas Damianu, who was one of my PhD students. He's now postdocing with me. I mean, I prefer this diagram. It looks much simpler. I actually got into machine learning because I liked drawing these things back in the 1990s. But nowadays, I prefer these things. And the idea with these deep models is that you don't just do latent variable models, but sort of Jeff's very persuasive argument that I enjoyed is that you have the idea of you get some abstract features, and then as you drop down the model, things get more and more detailed until you observe something in data space. So this might be an image, or this might be anything. This is the area where we can do we have the marginalization property. We can deal with massively missing data. So just to finish on as the last thing that was sort of interested in working on is how to, these are some samples from these deep models, is how to take these type of models and use them in health modeling. So what am I showing here? I want to show you just an illustration of this abstract feature thing. So this is a deep Gaussian process model being sampled from. And to try and illustrate the samples, I'm showing you a square at the top. And then this square is going through a Gaussian process. So it's been distorted in a nonlinear way. It's gone through another Gaussian process here, which has twisted some corner of that square. Now, the argument is that this is just the simulation of the model. We're not doing any data analysis now. But once that feature is in, it will stay in. So the rough argument is that anything that is in here, like this sort of point here, will continue to exist all the way down. You can't get rid of it. But as you drop down the layers, you get additional features added. The interesting question, and this was what really persuaded me, like I think Jeff actually at Microsoft Research in Cambridge, 2001, gave talks about models like this, and I sort of thought, yeah, I really understand now why you might want this type of architecture. The reason you sort of want it is because you don't quite know which level you're interested in. So is this the level here, the abstract features, where the clinician is interested in how disease is actually split up? So, disease manifests into different categories, such as, responders to treatment, non-responders to treatment, and then people who get worse. That's a typical thing that a clinician might think about a disease. Where does that exist in that model? That's some sort of abstract thing that the clinician thinks, and that's the thing we're trying to recreate so that the clinician can get involved with the model. But actually, the data we get is like an X-ray or something totally departed from that. It's sort of removed away from that. So this led to this idea of a...
Just to be clear, the parameters at a given layer are parameters in the kernel of a GP, and then you're composing maps that are sampled from the GP.
So when I do this talk to statisticians and I'm talking about the model, I call it stochastic process composition.
Right.
As a way of... And the reason, yes, good. And the reason we do it is because it means that the properties of the Gaussian, we get a much more general class of processes.
Okay, and you have some class of kernels with some parameters and let's say finitely many, and those are the numbers that are sitting at that layer, right?
Yeah. Okay. Yeah. So and the order of the number of those parameters is small. Right. So we only have sort of order. So in this model here, we would have approximately order 4 parameters, 6, 6. Not millions of parameters like you do in normal deep learning. We integrate all those out.
Choices in your kernels already, and then compose them, and then there's some parameters left that the parameters you're learning.
Yes, precisely. So back to how we sort of compose these Gaussian processes together, compose being the right word. This is the sort of thing we'd like to do. So this is what I call deep health. I've been calling it that for years. I mean, like 3 years now or something. And we can't do this. But what we can do is we can do subsets of this graph. So it's nice, I can point out people's PhDs. So Nicolo's PhD was to combine that and that with that in one model. So each sort of subset you take is actually like a whole PhD. There's a guy called Alan Saul who's working on GPs for survival analysis. Now, how are these coming in here? If we want this to be a latent representation of disease stratification at this level here, we need to include the sort of things clinicians are interested in. So our thought is that survival analysis should be directly related to that area, that level here. So that hopefully makes that level more interpretable because we can look at which dimensions are associated with survival. Because getting these latent variables interpretable is going to be a big challenge to integrate them with clinicians. In practice, when we've tried combining gene expression with survival, we get a lot of problems. We get those classic problems that survival information is super weak. So the model is trying to jointly model gene expression and survival. That worked well for Nicolo's project, but in Alan's project, that doesn't work well at all because the model spends all its time modeling the gene expression and ignores the survival model. So you're better off trying to input as covariates the survival data as we were doing before. But this is the sort of thing where we're trying to model it directly, which is what we'd like to do. We'd like to do that because often that data will be missing in a given patient example. So that's the sort of challenge, how you deal with that. This is weak information, and this is very detailed information, and you need to combine that together. We don't have good solutions. But ideally, we'd then also like to include social network information, music information, the clinical notes, so text data about what's going on with the patient, biopsies, X-rays, and they should come in at some level on this hierarchy. And the plan is that you can potentially do this, population scale, for all these different modalities of data. And when there's a new modality of data, you can introduce the modality and try and associate it, learn which level it's associated with. So you can learn the structure of these models as well. That's super ambitious, and we've got all we know we can do each of those things individually. we can't even pull survival data together with gene expression at the moment. So there are big challenges there. We actually learn that too.
And there is a benefit to using 4 nodes as opposed to 5 in a particular, or, you know.
Yeah, interestingly, and David Duverneau, who's now here at Harvard, did some nice work on this. It turns out that this is closely related to the properties of the underlying stochastic process you get. So the number of nodes you use at each level. If you were to expand the number of nodes to infinity, the whole thing would be a Gaussian process again with a particular covariance function. Adding these nodes in here leads to a sort of non-parametric, non-Gaussian process capability, which is the sort of thing we're after. I'm now thinking more of the stochastic process point of view, which was something came to later. The Jeff Hinton perspective on let's do deep was the original thing. So these things turn out to be very important parameters in terms of determining the properties of the underlying process.
Even if you're just going to, say, like Nicola's thesis or something, you're just looking at one output variable and 2 input variables, you still would benefit from having maybe more.
So in Nicolo's thesis, we learned, well, Nicolo will now correct me if I get his thesis wrong. So in Nicolo's thesis, we had gene expression as an output, so sort of order 30,000. We had SNPs as a genotype input, so potentially order 1 million. And then we actually inferred the environment as an additional, well, this was directly connected. We didn't really have this latent layer here. We were connecting these things to this. And we did it linearly to get the interpretability. I mean, if we'd done it non-linearly, I think no one would have published. You tried non-linear, right? And
they didn't publish it.
They didn't publish it, yeah. Because it's not interpretable. It's hard when you go non-linear with the Gaussian process. People, don't know how to interpret those things, even if it performs better.
Isn't there a lot hiding in the actual functional form of the kernels? I mean, here you have some. These nodes represent parameters in some functions that are not in the slide, right? So.
Yeah, I mean,
kernels P's. And isn't there like a ton of tweaking to do there and a ton of assumptions that are hiding in the choice of those kernels?
Maybe yes and maybe no. Covering all my options. Yes, I think that that's a really important choice. One's why it may not be as important as you might think is because if you're going to push one Gaussian process into another, you're effectively allowing nonlinear warping on the inputs of the Gaussian process. So this gives you a much larger class of functions you can consider.
And everything is in principle possible because they're like dense in the space. But like the typical types of things you'll see and like on what scale and are they like translation invariant, what structures do they have, are all determined by the choice.
We don't
kernel, right?
We don't do these sort of translational invariant things with these models that they do in image stuff at the moment.
The roughness.
Yeah, no, you would. Roughness also, again, I'm not too worried about it, but I am sympathetic to your point. I think it's true, and the problem is we can only do it tractably, efficiently for certain covariance functions.
Okay.
So the approximations require us to use certain covariance functions.
Okay, so it's driven partly by XP.
Yeah, it's driven by current capabilities, yeah.
So this vision of a deep learning process as very abstract features and then building up more and more interpretable, maybe more interpretable ones or getting down to level data, this feels, I mean, the picture's quite clear in the image classification task or the square example you showed us. But now you're talking about integrating all kinds of different data into this picture, and you've restricted yourself to a vision which is very linear. It has one parameter in this notion of abstraction, and it feels to me like if you want to squash all this together, there will not be just one parameter. There's almost a manifold.
You mean one parameter in terms of? In terms of,
I mean, the depth. You're talking about depth. But this feels like
you want abstractness itself to be multiple.
Yeah, I want a new type of data to not just fit at one depth, but to perhaps have multiple.
That's allowed for. That's allowed for. So I've drawn it like this because it wouldn't. The idea of the hierarchy of features wouldn't come in. But there's no algorithmic. There's no I don't want to say theoretical. There's no issue with trying to do that architecture. You could have an architecture do that. And be careful by saying there's one parameter because there are actually infinite parameters, but we integrated them out. So I think it's dangerous to summarize it with like the depth because there's an awful lot going on in terms. There's an enormous amount of uncertainty being sustained in this model, and that's why, and that's important if you're going to do if you're going to do data that is. My belief is that you need to sustain that uncertainty if you're going to be in this zone where the system you're trying to model is really, really complicated and the amount of data you have is scarce relative to that complexity, which is the domain that the current generation of deep learning algorithms do not perform well in. And we do perform well in that domain when we do little experiments. Okay, and that's kind of it. So I slightly overrun at the end there. There's sort of more stuff if I'd emphasize different things, but that's it. So the key lesson is that, well, I believe in models like this. I kind of think the technologies are in place, not that we can do it like tomorrow, but that we know that we can fit models of this scale. We can do all the things we just talked about, learning the different structure of those models, scale them up to millions of data. There are problems about, like, well, my belief is that if you get the likelihoods right, you can integrate survival type data, but you still get challenges in that sort of domain, and we haven't sort of yet resolved them. And the broad work in my lab is most people's work you can actually summarize by trying to piece a couple of these things together and do something useful in the interim before we can solve such a large-scale model.